Welcome back everyone to this lecture where we're going to be discussing the theory and intuition behind gradient boosting. Gradient boosting is a very similar idea to adaptive boosting or AdaBoost, where we're still going to take a bunch of weak learners that are created in series, that is to say the next weak learner learns from the mistakes of the previous weak learner, in order to produce a strong ensemble model at the end. And in fact, we could use gradient boosting with other models that are not decision trees. It just happens to work best with decision trees, which is why, again, you typically hear about boosting with decision trees. Now, gradient boosting makes use of the residual error for learning, which is different than what AdaBoost does. So let's talk about the main differences to keep in mind as we learn about gradient boosting. In gradient boosting, we are going to allow for larger decision trees to be developed versus the stumps that we were developing in AdaBoost. You should also note that when you see the learning rate coefficient in the formulas, that's actually the coefficient that's applied to all the weak learners. So all the weak learners have the same learning rate coefficient, unlike AdaBoost, where you had a separate coefficient for each particular weak learner. The other thing to note is that the gradual series learning is based on training on the residuals of the previous model. So let's discuss that idea because that's the main way gradient boosting is the meta-learning algorithm based off those residuals. To show this, it's typically more useful to take a look at a regression example versus a classification example, although we will show you at the end the differences between regression and classification. But let's keep in mind a gradient boosting regression example where we're trying to predict the price of a house. And we have a bunch of features like the area, number of bedrooms, number of bathrooms, and then the historical trading price. So as we conduct our training, what we're going to do is we're going to train a decision tree on the data. So we take a decision tree and we train it on this particular data set. And then we should note that this is not just a stump like AdaBoost, but it can be a larger decision tree. And then we get some predicted y hat value. So recall price here is the y, that's the true label, and then we end up with a prediction like y hat. And you can see just a single decision tree is actually not performing super well. In fact, it predicts 509,000 for each of these different houses, which is actually just the mean value of the houses. So not a super great decision tree. The next step in gradient boosting is to then calculate the residual or error known as E, where it's simply calculated as the true y value minus your y hat prediction. So here we can see we have an error of negative 9,000 for the first data row because we predicted over 9,000 from the true price. And then we have negative 47,000 because we predicted over by 47,000. And then for the last prediction, we were off by under 56,000. So note there the signs because we're saying true y minus y hat, which leaves us this residual term. And this residual term now inherently has information about how the first decision tree performed. Then what we're going to do in the gradient boosting process is we create a new model. However, this new model is now not trying to predict y based off the features, it's trying to predict e, that residual term based off the features. So now we're going to create a new model to predict the error term, that is this e column, instead of trying to predict the y column. So we get a brand new decision tree, and this decision tree is now optimized to try to predict the error column, not the original y column. And we will call this new prediction F1. Now I want to be clear about what's happening right now. This new decision tree model is still using those original X features, but instead of trying to predict y, it is now trying to use those same features to predict the residual from the previous model. So it's really focused on how can I best predict E given the original features. And so its predictions are then labeled as F1. You'll notice it's not able to perfectly predict the residual E, so it comes up with its best approximation or estimation as F1. In the exact same way, the previous model came up with its best estimate of y as y hat. So we're using the same features, except we've changed our label to, instead of being y, to be the residual based off the previous model. And that's the key word, based off the previous model. So we're learning in series. Now what can we actually do with this F1? And this is where the gradient boosting occurs. What we're going to do is we're going to update our original prediction for y using the error prediction. So we'll use the formula F1 is equal to y hat plus this F1 prediction. Essentially, we're adjusting our original estimation based off the residuals of the previous models. So we'll say our stage 1, or kind of stage 2 really, prediction of f1 is equal to the original y hat adjusted by this new f1 prediction. And you'll notice that if we begin this adjustment of saying y hat plus f1, we're actually now getting closer to the original y. So note now, instead of predicting 509,000 for the first row, with this new adjustment of f1, we're now predicting 501,000. So we're actually getting closer to the original label by adjusting off the residuals of the previous model. So we're learning in series from previous models' mistakes and hoping to adjust and improve off those models. And we can continue this process in series. So that means the formula really for the gradient boosting process is just saying that f of m is equal to the result of f of m minus 1 plus little f of m, essentially just adding in the new approximation of the residuals from the previous model. And keep in mind, the way we can adjust the gradient boosting process is by using a learning rate. So we actually end up multiplying that residual prediction by a learning rate. And this learning rate is going to be the same across all the models, unlike AdaBoost, which had its own special coefficient for every single weak learner. Instead, we have a broad learning rate that gets applied to all the weak learners throughout the series. And this is something you can adjust. As you can imagine, the smaller you make this, then the more time it's going to take in order to create more trees to really encourage new results in the model. So let's talk about the actual gradient boosting process step by step. What you do is you first create that initial model that's predicting directly that y and outputs that y hat. And then we train another model on that error, where we define the error as y minus f of 0, or that y hat prediction. And then what we're then going to do is create a new prediction. We're going to say capital F of 1 is equal to f of 0, or lowercase f of 0, plus the learning rate times this new prediction f of 1, where that new prediction is that adjustment on the residual. So you essentially have your original y hat prediction, and then you keep adding and subtracting to it based off your learning rate and the approximations of that residual. So you're continually, hopefully, improving your original y hat based off the next series of residual estimators. And you can repeat this as needed, which ends up giving you the capital F of m is equal to lowercase f of m minus 1 plus the learning rate times the current f of m. Now you should note, for classification, we can just use the logit as an error metric. And you're already familiar with these formulas if you've gone over the logistic regression lectures. And if you are a little fuzzy on these, go ahead and review those logistic regression lectures, because we do go deeply into using logistic regression there and how we can measure classification error. But this is how you would predict y hat and be able to measure the error based off a classification, essentially just measuring your logic or probabilities. Okay. Now, again, I mentioned this already, but I want to be clear here. The learning rate is the same for each new model in the series. It is not unique to each subsequent model, unlike AdaBoost's alpha coefficient that we saw earlier. And gradient boosting should be noted that it's also fairly robust to overfitting, just as we saw with Random Forest and AdaBoost, which really allows for the number of estimators to be set quite high. And by default, we set them to 100. So what's really nice about these more advanced tree-based methods, whether it's Random Forest, AdaBoost, or Gradient Boost, you don't really need to worry too much about overfitting, because it takes a lot of trees before you reach that point. So typically you just get no improvement in the performance, and so there's no need to continue on to the overfitting stage. So what's the actual intuition we can grasp from gradient boosting? Really what we're doing is we optimize the series of trees by learning on the residuals, which forces subsequent decision trees to attempt to correct for the error in the previous trees, since they're just trying to figure out that error based off the features instead of going straight for that y hat prediction. Now, what's the actual cost here? Why don't we just do gradient boosting all the time? The real trade-off is training time. Since a learning rate is set to be between 0 and 1, that means a very low value would mean each subsequent tree has very little say, because you're multiplying it by a very small number, meaning that more trees would need to be created, causing a longer computational training time. So we often think of learning rate as a trade-off between learning rate versus number of estimators. The lower your learning rate, the more number of estimators or decision trees you're going to need in series to really have an effect. And then the larger the learning rate, that means those subsequent decision trees are going to have a large effect, which means they'll just take a few decision trees to really start heavily modifying that y hat value. And if you make it too large, you'll not actually get the best or peak performance on your prediction metrics because you're not taking the time to really learn off the residuals to see what features were important for the next coming decision tree. So keep that in mind. It's usually something you have to grid search for. Okay, let's go ahead and explore gradient boosting in practice in the next lecture. I'll see you there.